This episode of Real Engineering is brought to you by CuriosityStream. Watch thousands of documentaries for free for 31 days at curiositystream.com/real engineering. This year, the F-35 is finally set to close its 27-year development phase and move towards high-volume manufacturing, the culmination of 27 years of design and development from its manufacturer, Lockheed Marten. 27 years of development crossing the finish line in the midst of a political power struggle in America. This is, after all, the most expensive weapon system in the history of humankind. Costs have inflated as a result of the American military-industrial complex, where the intertwining of politics, economy, and the military industry encourages companies like Lockheed Marten and Boeing to not vertically integrate their companies, as a means of spreading jobs across America and thereby increase political support for these programs and the politicians that approve them in Congress to win contracts. We could deep dive into these muddied waters of politics, but this channel is about engineering, and the development costs of the F-35 would be astronomical even without these issues. So let's explore the design of this plane and see whether its price tag is really worth it. From the start, the F-35 sought to be the jack of all trades, an air superiority machine to replace the Air Force's F-16s and A-10s, a stealth fighter taking the lessons learned from the B-2 program and improving upon Lockheed's previous ventures into stealth technology with the F-22 Raptor and the F-117 Nighthawk, a carrier-capable fighter to replace the F-A-18 Hornets of the Navy, and perhaps most audacious of all, it would take on the challenge of vertical landings, taking over from the British AV-8B Harrier. Taking on all these advanced technologies and combining them into one plane was never going to be an easy or cheap task, and the program was made even more expensive by what was initially intended to be a cost-saving measure. This plane would be developed as a joint venture between 3 US military branches, the Air Force, Navy, and Marines, a single plane for each branch of the military. The program was named the Joint Strike Fighter, and its goal was to produce a next-generation plane that could replace fighter, strike, and ground attack aircraft of not just the United States, but all of its allies. Unlike the F-22 Raptor, which is a US Air Force exclusive plane, the F-35 would be commercially available. The Joint Strike Fighter program began life as a competition between McDonnell Douglas, Northrop Grumman, Lockheed Marten, and Boeing, with Lockheed and Boeing going on to develop prototype aircraft as finalists in the competition, both eager to win what was sure to be one of the most lucrative contracts they would ever sign. Boeing's aircraft, the X-32, was an odd-looking aircraft, featuring a massive single air intake that made it less VTOL and more VLOL. Its looks alone may have stopped it from winning this valuable contract, but what really held it back was Boeing's decision to create 2 prototype planes, one capable of supersonic flight and one capable of vertical takeoff, using the same vector thrust as the Harrier, which it was supposed to be replacing. The engine used in the Harrier is similar to a traditional jet engine in that it consists of a low-pressure compressor fan, a high-pressure compressor, a combustion chamber, a high-pressure turbine, and a low-pressure turbine. But its outlet nozzle placement is anything but traditional. 2 outlets are placed immediately after the low-pressure compressor, with another 2 ducting air from the higher-pressure turbines. In vertical thrust mode, the nozzles point downwards and allow the plane to balance precariously on these 4 columns of air. The Harrier was not an easy plane to control in this flight mode, and on more than one occasion, turbulence from its own downwash caused the plane to flip over onto the cockpit during landings, killing the pilot. A large part of these control issues can be attributed to the proximity of the control nozzles to the center of gravity of the plane, giving them less mechanical advantage to manipulate the plane's attitude. The Harrier did have small roll control nozzles on the tip of each wing, but the control for these were entirely manual, placing the incredibly unstable control mechanism into the hands of a human that needed to focus on various other factors when landing. The X-32 used many of the same techniques to achieve vertical thrust, but improved on many of the Harrier's shortcomings. Instead of using the same nozzles for cruise and direct lift, the X-32 would close valves for each when needed. In normal flight, the cruise nozzles would open, allowing the thrust of the jet engine to be directed efficiently through the rear of the aircraft. Then, during transition, this nozzle would close and force air through the direct lift nozzles. They placed larger roll control nozzles further from the plane's center of mass and also employed a cold air screen placed just forward of the lift nozzles. This was intended to stop hot, turbulent air from the direct lift nozzles from entering the front intake, which was a massive issue for the Harrier as it landed. Jet engines need cold and smooth air to operate at maximum thrust, which was difficult to get when landing and directing the entirety of your thrust directly at the ground. Despite these improvements, Lockheed ultimately won the contract, impressing the Joint Strike Fighter program with their lift fan system. The engine thrust here, once again, exits a single exhaust nozzle during normal flight, but when the show begins, the X-35 was capable of some incredible transformer-like changes. Hatches opened on the top and bottom of the aircraft, revealing 2 contra-rotating fans. Another 2 little doors opened beneath the wings, exposing 2 additional exhaust ports that control the plane's roll. Finally, as the plane begins to slow down, the cruise nozzle would begin to pivot downwards, transitioning the remaining thrust of the jet engine from horizontal to vertical. The lift fan solved many of the same issues that plagued the Harrier. The lift fan produced the majority of the vertical thrust and it did not heat up the air significantly in the process. The roll control had significantly more mechanical advantage and divvied the majority of the control over to a computer. Perhaps most influential in their success to winning the contract, this prototype was capable of both vertical landings and supersonic flight. This was the kind of innovation the Joint Strike Fighter program was looking for. The lift fan is essentially a turboprop engine like something you would find on an Osprey. The propellers are driven by a driveshaft connected to the jet engine turbines, which can be disengaged during normal flight. This means the lift fan is dead weight during cruise, but what it adds in weight it more than makes up for in lift. Combined, these propulsion methods can produce 185 kilonewtons of lift. The Harrier could only manage 106. This increase in direct lift capabilities was vital to making the F-35 a worthy successor to the Harrier, as one of the Harrier's greatest weaknesses was its limitations in maximum takeoff and landing weight. The Harrier, like the F-35B, mostly operated in short takeoff and vertical landing mode. The Harrier would point all 4 of its nozzles at about a 45-degree angle, allowing it to produce both horizontal and vertical thrust to take off from shorter runways. This allowed it to take off with considerably more weight than it could land with in a vertical landing. The empty weight of the F-35B may be 13,154 kilograms compared to the 6,340 kilograms of the Harrier, but it more than makes up for that with a maximum takeoff weight of 31,800 kilograms compared to the Harrier's 14,100 kilograms. That's an extra 11 tons of weight available to the F-35 for fuel and ammunitions, something the Harrier had little space for. So, the F-35 is more than a worthy successor to the Harrier, a plane which fetched about $24 million per unit in 1996, or about $39 million adjusted for inflation. So, incorporating VTOL to the F-35B was just one of many design challenges that pushed the price of the program up. Ironically, despite Boeing's dual prototype entry being a sticking point for the JSF program, the F-35 now comes in 3 variants, each tailored for different branches in the US military. The F-35A is customized for the US Air Force and as such has been designed to take off from conventional runways, allowing it to scrap much of the heavy equipment needed for the F-35B, the Marines variant. The Marines do not operate out of large aircraft carriers like the Navy, and as such, their ships, like the Wasp-class amphibious assault ship, have often been referred to as helicopter carriers, as no plane other than the Harrier or Osprey have been able to use them. This is not the case for the Navy, who have large aircraft carriers at their disposal. The final variant is the F-35C, which has been designed to satisfy the Navy's requirements, having wings that are about 40% larger than either of its sister variants, and its landing gear is much heavier and stronger. Both of these features were included to allow it to land and take off from aircraft carriers without the need for the vertical propulsion like the F-35B. The larger wings not only allow the F-35C to have the largest fuel capacity of the three, but also give it much better lift at slower speeds, making landings and takeoffs much easier on the deck of an aircraft carrier, while the heavier landing gear allows the plane to survive the rough landings associated with the arresting wire landings on aircraft carriers. The F-35C also incorporates folding wingtips to allow for neat storage inside the ship. This expansion into 3 variants has been a huge source of increased costs, and the program likely could have dramatically reduced on spending had it just designed 3 different planes for 3 different branches. Trying to squeeze the needs of these 3 military branches into a single airframe was never going to be an easy task for the R&D division of Lockheed Martin, and forced them to make some concessions in design that have limited them in other areas. The brunt of criticism directed at the F-35 is its shortcomings in dogfighting capabilities. Headlines of the F-35 losing simulated dogfights to Cold War era F-15s and F-16s grabbed many people's attention and were used to detract from the F-35's advancements. We only knew about these issues as a result of a report that leaked to the press. Let's take a look at that report to see what this test pilot thought about the F-35A he flew. The primary flaw this pilot highlighted was the F-35A's poor energy maneuverability, meaning the F-35A struggled to maneuver without expending a significant amount of its kinetic energy, which is a problem I discussed in more detail in my fighter jet instability video. The primary design aspect the pilot pins this on is the smaller wing area and the weaker afterburner thrust of the F-35 in comparison to the F-15E he was accustomed to. Essentially, their issue with the F-35 was that it depleted its kinetic energy store quicker than its competition. We have no reason to believe this pilot was wrong in his findings, so what does this mean for the F-35? It is important to note that this was not a fully functional version, missing software enabling the plane to detect its foes before they can detect it, and was missing radar-absorbing paint. On top of this, the F-35 is not short of trained military aviators who praise the F-35, like US Marine Corps Major Dan Flatley, who helped design the combat training program for F-35 pilots, and he has chalked up these issues to old habits of pilots who have spent significant portions of their lives dedicated to older generation planes, which were designed with a different philosophy in mind. Since then, the F-35 has performed phenomenally in simulations with reports up to 20-1 KDRs. Other pilots who have had more time to become accustomed to the F-35 had more positive things to say, like John Beasley, the chief test pilot of the F-35 with 22 years of experience as a test pilot at Lockheed Martin, and was involved in the development of the F-117 Nighthawk and the F-22 Raptor. He claims the F-35 can outmaneuver any US fighter except for the F-22, which was designed specifically as an air superiority machine and again is not available for purchase outside of America and actually has a higher unit cost than the F-35 at about $150 million. It's hard for me to make a judgment call on this because I have as little information as any other civilian. But honestly, outside of this one report, most pilots who have flown with the F-35 sing its praises. John Beasley also makes an important note. Air combat has always relied on stealth, whether it was World War I pilots diving from the sun at their backs, or modern fighters using advanced radar masking design. Because in the grand scheme of things, in a dogfight, the real stat that matters is who sees and shoots first, and the biggest factor that contributes to that are the onboard sensors and stealth. The thing that really sets the F-35 apart is its suite of sensors and computer guidance systems, which have been integrated with the user interface of the aircraft unlike any other plane in the history of mankind, while sharing that information with the entire force. This is what truly makes this plane something to be feared, and it all starts with this, a little transparent faceted sensor suite containing the infrared imaging and tracking equipment of the aircraft. But those are not your typical windows. Those are made of sapphire, a notoriously expensive gemstone, one of the few materials that is both hard and durable, but also transparent to a broad range of wavelengths. The imaging data from these sensors can even be fed into the pilot's helmet visor, which has been enhanced with augmented reality technology. This helmet alone costs $400,000 and enables the pilot to look straight through the aircraft and see at night without having to wear clumsy night vision goggles. The helmet also feeds in data from the multitude of other sensors like the advanced high-frequency radar in the nose of the plane, along with data received from sensors from other aircraft and ground-based units. The data does not feed into the pilot's AR helmet unfiltered though. It passes through the onboard computer, which performs all the necessary filtering and data analysis and only presents the pilot with the information he really needs. This technology is so powerful that even an unarmed F-35 would greatly boost the combat effectiveness of its allies. But detection is just one step of that goal of shooting first. Not being detected is just as important. Incorporating stealth was just another design challenge and is likely the source of much of the unexpected costs. Let's first clear something up. Despite what you may have otherwise heard, stealth does not render a plane undetectable. Short of not physically existing, everything is detectable. If we can find and analyze planets billions of light years away, we can detect a plane flying directly overhead. Stealth's purpose is not to make the plane invisible. It serves to complicate and delay the enemy's detection of an aircraft. Stealth has proven itself invaluable over the past 2 decades, prior to the F-35's inception. The F-117 Nighthawk flew over 1,300 missions over Iraq during the Gulf War, scoring direct hits on over 1,600 high-value targets without losing a single aircraft. But it was far from perfect. Lockheed knew this all too well as the manufacturer of the F-117. In 1999, a Nighthawk was infamously spotted by radar and subsequently shot down over Serbia. The pilot survived, but the plane crashed and remained mostly intact, handing over a valuable technology to the Russians to reverse engineer. Stealth serves a single purpose, to avoid detection, and the F-117 failed here. But it was developed using 1970s era computing technology. Its panels were flat and faceted simply because we did not have the computers capable of analyzing more complicated shapes to optimize stealth. Early attempts at stealth worked under a fairly simple theory. Radar works by sending out pulses of electromagnetic waves and waits and listens for reflections. The idea behind stealth technology is to not reflect those waves back at the emitter and thus avoiding detection. This is why the F-117 is shaped like this. Each panel has been angled and placed in a way to minimize how much of this energy it will reflect back to the sender. It was also coated in a paint that would help absorb some of that electromagnetic radiation. Opponents of stealth technology, despite its proven track record, are quick to point out that long wavelength radar is capable of detecting stealth aircraft. The same kind of radar that detected the F-117 over Serbia, and the same kind of radar used in the Battle of Britain. While this is true, these stealth aircraft are optimized to avoid detection of higher frequency radar. Those opponents rarely mention that low frequency, long wavelength radar do not provide high fidelity measurements and struggle to pinpoint the location of the aircraft. This makes them effective early warning systems, but entirely useless for directing missiles. While this is certainly not useless, it's not particularly useful in air-to-air combat. Had the F-117 Nighthawk on that night been escorted by its usual squadron of electronic jamming prowler aircraft, the missiles may well have never got a lock. This was made worse by the fact the aircraft was flying a regular flight path, and so the Serbians knew where to look. Topping this off, the F-117 was designed in an era before sophisticated computational analysis was available, and so it took this relatively simplistic flat-faceted form. The B-2 and F-22, however, greatly improved on the technology, utilizing complex curved shapes which no human could hope to calculate the radar signature of, and they have never been shot down. The curves diffuse those radio waves in many directions, rather than reflecting it all in one direction, which makes it easier to detect by receivers listening in locations separate to the emitter, a fairly standard practice today. The F-35 uses the same complex curves to avoid detection by these high-frequency radars, and this is likely one of the things driving its development costs up the most. Stealth technology requires precision beyond any other type of manufacturing. This is manageable at small-scale production like that of the B-2 and F-22, which had very small production runs. The F-35, however, is expected to be a mass-manufactured aircraft that foreign allies with shallower pockets than the US military will be willing to pay for. Creating a manufacturing line that requires this level of precision was never going to be cheap. Panels cannot have gaps between them, they cannot be malformed, a single scratch on the radar-absorbing coating will require an entire repaint of the part. Small manufacturing defects have caused recalls on multiple occasions. Lockheed is only now starting to comfortably roll the plane off the assembly lines, and that is reflected in the lowering price of the aircraft. The latest batch of orders have reduced in cost by 5.4% for the F-35A, 5.7% for the B variant, and 11.1% for the F-35C, leaving us with a unit cost of $89.2 million for an F-35A, $115.5 million for an F-35B, and $107.7 million for an F-35C, with the F-35A expected to drop by a further 4.7% to $85 million by the end of 2019. This sounds like a shitload of money to the average person like me, but we get a clearer picture of these costs when comparing to other 5th generation fighters like the F-22 Raptor, which cost $150 million per unit. Or even looking at the other aircraft it's going to be replacing. I think it's fair to say that we've established that the F-35 is a worthy successor to all of these planes, which individually come with their own hefty price tags. But the F-35 manages to combine the capabilities of all these aircraft into a single plane. Yes, the development costs of this plane have been astronomical. That cannot be denied. But much of that money has gone directly back into the American economy. Then, when you consider that the plane is expected to sell up to 4,600 units by the end of its lifetime, nearly identical to the total F-16 sales figures, this will inject more money into the American economy, considering a large sum of these orders will be from international exports. So, is the F-35 worth its $115.5 million price tag? As an Irish citizen, that's not for me to decide, but I can say one thing. This is a fascinating plane with astounding capabilities. This may have been a heavy price to pay, but what isn't is a subscription to CuriosityStream at a price of just $2.99 a month. With that price, you will get access to thousands of documentaries and non-fiction titles like this fantastic History of Weapons series. Not only that, you will also get free access to Nebula, the streaming video platform built by and for independent creators like Tierzu, Lindsay Ellis, Minute Physics, Wendover Productions, and my new channel, Real Science, which just launched last week. Where CuriosityStream is all about big budget non-fiction videos, we're building Nebula because we want a place for educational creators to try out new content ideas that might not work on YouTube. I'm currently working on a Logistics of D-Day series, and the next episode of Real Science is already available on there, but won't be on YouTube for another month. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering Real Engineering viewers free access to Nebula when you sign up to curiositystream.com/Real Engineering. By signing up to CuriosityStream, you'll be helping not just me, but the entire educational community, as we work together to build a place where we can create content like my Logistics of D-Day series that would just be too risky to rely on YouTube. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit, and Discord server are below.